Okay, so in this video, we're going to be talking about measures or measure of variability. So what we're really talking about here is once you have a data collection, all right, and let's say you just did it like a little dot plot here, all right, and what you noticed was you had a couple dots, and we'll make this nice and symmetric, at least as best we can, all right. Right here we can clearly see that is going to be our mean. That's going to be in the middle. When we talk about variability, what we're really asking here is how much does the data vary within itself? Okay? So notice here, I'm just drawing all these like little arrows and everything because what I'm really saying is, okay, now that we've collected the data, how much does the data vary? Within itself. Okay? Now, there are different ways that we can actually do this. The first way that we're going to talk about, which really isn't the best, but it's called the range. And to calculate the range, all you do is you take your max value and you subtract your minimum value. And that's just going to tell you the range of data. That's it. Now, obviously, it's sensitive to outliers. And I'm pretty sure you've heard me say this before, you lose the richness of the data. So you lose information. All right? A great example of this would be something along the lines of what I have here above, okay? So notice here I have all this data that's been collected. Let me just draw it again. I hate all those little errors. It's driving me crazy. All right. And let's say, for example, you have this point all the way over here. Just one little one all the way off to the right. When you're calculating the range, all you're going to use are the extreme values, the maximum and the minimum. Notice you lose all this in between, okay? So the range, although it's used, it doesn't really tell us too much about how the data varies within itself. The most common way to measure variability is called the standard deviation. And this is the most common. This is what you're going to see a lot. This is what we're going to be calculating. All right. And this, or the standard deviation, is defined as the measure of how much the data value, sorry, I forgot the word the, deviate away from the mean. Okay? So before I give you the formula, I want to show you a picture. So here we have two bell-shaped curves. Okay? And they vary. I don't want to say this here. They vary differently. That doesn't, for me, it's like not making sense right now when I say that. The key to remember here, in fact, let me just do this. I think this is better because this is what I have in your notes. In both situations here, they have the same exact mean. However, their deviations are very different. The red bell-shaped curve has a very low deviation. And that's because the width of this bell is very small. It's very tight. However, the black line, or the black bell-shaped curve, has a very high deviation. And that's because the distance, or the width of the bell itself, is very wide. All right, so we would expect to have a very high deviation. Okay? Now, to calculate standard deviation, we give it the letter S, and it's a lowercase s, and it's going to be defined as the square root of the summation from x minus x bar squared all over n minus 1. Now, this should look very familiar, okay? Because what the standard deviation really does, okay? The standard deviation, it takes the distance of all values away from the mean and it averages them. So if you're looking at the I was going to say, if you're looking at the screen right now, x minus x bar is a distance. Okay? Now, you're going to add them all up. So I'm going to highlight the sigma symbol. So you take x minus x bar, you square it, you add up all those values, and then you divide by n minus 1. You have to penalize yourself one of these values because x bar is estimated, so you're going to exclude that from your formula. So that's why it's n minus 1. So you have x minus x bar squared. There are all your distances. You add them all up and divide by the total number of distances that you have. So it's nothing more than just the average of all the data points. It's the average of their distance away from the mean. Now, the hardest part about calculating standard deviation is just keeping things organized. So in the guided notes, I have just an example. So we're going to find data speeds Let me write it again. Let's find the standard deviation of data speeds times listed below. So what we did is we just kind of did, like a speed test at random times throughout the day. And here's what we found. The first time we did it was 38.5. Then we have 55.6. Then we have 22.4, 14.1, and 23.1. Now, like I said, the easiest way to do this is just to create a table, keep everything organized, because what you're going to notice is when you use the formula, S equals the square root of the summation of x minus x bar squared all over n minus 1, you're going to have to find first the mean, and then second, you're going to have to find the distance of every single data point, 38.5, 55.6, and so forth, away from the mean, and square that number. So in the guided notes, I have a table that kind of looks like this. And then at the very bottom, it says like summation. And what you're going to do is you're going to find the numerator first, then the denominator second. I'm going to divide those two numbers and take the square root. So to help us with this, I like to work smarter and not harder. So I'm just going to use Excel. And Excel is a very powerful tool. It is a spreadsheet. It is not. Some people think. I've heard some people say, "Oh, it's like a statistical software package." And while I'm not gonna argue the nuances, Excel is a spreadsheet. So, It's really good to understand how it works. It allows us to do math very quickly, organize data, and there's other things you can do too with it. So notice here I'm just titling my columns x minus x bar, and then x minus x bar to the second power. Okay? And then I'm going to type in all of my data values. So we have 38.5, 55.6, 22.4, 14.1, 23.1. Okay? Off to the right here, in cell E, I'm just going to write the mean. And then directly to the right of that, I'm going to type in a formula. Now, excuse me. If you want to calculate, or if you want to calculate anything in Excel, you have to put an equal sign first. So we put an equal sign, and what we're going to do is we're going to type in the word average. So AVER. And notice that you have all these different functions that kind of popped up. And if you leave your cursor on them, it'll tell you a little description. So for the very first one, it says returns the average or their arithmetic mean of its argument, which can be numbers, names, arrays, references, whatever. So all we're going to do is just double click on this. And then it's going to say, okay, give me number 1, comma, number 2, comma, number 3, and so forth. So what I'm going to do is I'm going to take my cursor. I'm going to left click and hold it in and drag all the way down. And what I just told my computer to do, and I'm going to end the parentheses, I just told the computer, find the average, and the numbers I want are in cells A2 down through A6. And as soon as I do that, I hit enter, and I come up with 30.74. Okay? So there's our mean. Now, what we need to do next is we're going to take x minus x bar. In other words, I'm going to do some math. So I want to hit equal sign, and I want to take my x value, which is 38.85, and I want to subtract my mean away from that. So I'm going to click on 30.74. Now, here is what I'm about to tell you is extremely important. You want to go ahead and do this for every single value, okay? However, this 30.74, you need that number to stay exactly where it is. All right, let me show you what I mean, because I'm telling you we're going to make mistakes. So right now, I get 7.76, which is correct. Now, if I wanted to, I can copy and paste this formula just by moving my cursor. So if you notice my cursor right now is a plus sign, and if I move it over top of the number, down to the lower right-hand corner, it turns into a black plus sign, okay? Also, if you it's kind of hard to see. Maybe can I zoom in a little bit? Maybe we can see it a little bit easier. I think that's better. In the lower right-hand corner of this cell, you're going to see this little dot, a little green dot. It's very small. But if I put my cursor over top of that, it turns into a plus sign, a dark black plus sign. So I'm going to left click, hold it, and drag it straight down. And what I've done is just calculated what I think is the distance between every x value and the mean. However, you're going to notice that in cell B3, B4, B5, and B6, they're the exact same values. So something should be telling you right now, something's not happening here. Now, the easiest way to kind of figure this out, if you look up top, and that little, we call it a function bar, you're going to notice that it's taking cell A6 minus F5. Also, if you look down below, it's color-coded. So A6 is blue, F5 is red. So A6 is 23.1. And if you look all the way to the right, F5, there's nothing there. So what it's doing here is it's subtracting 23.1 minus 0. And 23.1 minus 0 is 0. We know we need to subtract 30.74. So how do we do that? Well, if you come all the way back up to your very first cell here, which is what we did. Let me get rid of these down below. Actually, I don't want to delete the column. I just want to, there we go. No, come on, clear contents. There we go. So if we come all the way back here, back up here, and we know this is correct. 38.5 minus 30.74 is 7.76. In order for us to keep that 30.74 static, meaning we want to take every single one of these x values and subtract it away from it, what we have to do is put a $sign in front of the f, and then a $sign in front of the 1. And now, we're still going to get 7.76. However, what I just told Excel is to go ahead, keep that value. And now when I go ahead and scroll down, I get all the appropriate values, which is what I should get. For x minus x bars squared, I'm going to hit equals because I want to do some math. And I need to take this column and just square it. Because I've already calculated x minus x bar. All I want to do now is just square all those values. And drag it all the way down. Beneath this, I'm going to get total. And then I'm just going to hit equals. And remember, total means addition. So we're going to sum up our values. So we just type in the word sum. Double click on it. And just sum up all those values right there. So our sum, in other words, our numerator value is going to be 1083.052. So I'm going to take all this information and I'm going to really clean this up. And I'm going to make it look actually really nice. Because I am just weird like that. I like things to look pretty and organized. I'm sorry. All right, so now I'm just going to copy and paste this back into our notes. So in your table, if you've been following along, that's what we have right here. Here's our table. Okay? So according to the standard deviation, we have our numerator, which is 1083.052. Now, what's really nice about this data set is very small. It's only 1, 2, 3, 4, 5 values. So doing this by hand will not take a lot of time. The hard part is, what if you have 100 data values? Now you want to start, using a tool to help you. So we need to divide this by n minus 1. Since we have 5 data values, it's going to be 5 minus 1. So S is going to equal the square root of 1083.052 divided by 4. So if you just give me a second here, I'm going to go ahead and calculate this in my calculator. So we get 1083.052 divided by 4. And we get 16.45 rounded to the nearest tenth, or nearest hundredth. So what this tells me is that given the data that, given the data that we've collected, our standard deviation, the average distance of all the data values away from the mean is approximately 16.45. All right. Now, when you look at the data, you need to kind of think about, okay, well, is 16.45, is that a very large number or a very small number? And the only way to really do that is just have an understanding of where these numbers lie on a number line. So because 16.45 isn't that large of a number, I would say that that this data value is kind of close to each other. It doesn't have to be perfect, all right? In fact, if you really think about what we're talking about with the standard deviation and it being a measurement away from the mean, If all of your x values are the same exact number, then your standard deviation is equal to 0 because you're not deviating anywhere away from the mean. All right? Now, another way that we measure variance is within the data itself. So the standard deviation gives us a distance away from the mean. And then the other type of variability is called the variance. And a way to think about the variance is how I'm going to write it like this: how much the data varies from all its values. Okay? Sometimes we say that the variance is the sum of the squared deviations of the measurements about their mean. Okay? Now, there is a relationship between the variance and the standard deviation. I mean, if you think about what we just wrote here, the variance is the sum of the squared deviations of the measurements about their mean. The standard deviation we defined earlier as the square root of the summation of x minus x bar squared all over n minus 1. And the variance is the sum of the squared deviations. So, if I squared my deviation, then actually, let me show it like this. If we take our standard deviation and we square it, meaning we square the formula left and right sides, what we get is the variance. And here is the formula for variance. So if you can calculate the standard deviation, square that number, and you get the variance. So I'm just going to scroll up here a little bit. I'm going to change my color to red. The variance for the data set that we have here is going to be 16.45 squared. So if I just take 16.45, give me a second, and square it, I get 270.8. And all that tells me is just how much does the data vary within itself. Now, I do want to go over some properties of the standard deviation. Oh, let me get out my black marker again. So properties of S. Okay. First, it's a measured horizontal distance. Once we start talking about z-scores and everything, you're really gonna see where this horizontal distance actually kicks in. The standard deviation is always going to be greater than or equal to 0, which means it's positive. A large S implies greater amounts of variation. It is very sensitive to outliers. I mean, if you think about it, the mean is extremely sensitive to outliers. So, the standard deviation, which includes the mean in its calculations, will also be very sensitive to outliers. It will have the same units as the mean. So, if the mean is measured in pounds, then standard deviation would be measured in pounds as well. And we call this a biased estimator. Once we get into sampling techniques, or sampling, which is in, I think, Chapter 6, I will go ahead and define and show you how we determine if something is a biased or unbiased estimator. Biased just is exactly what it implies. It kind of skews the data a little bit. Unbiased estimators do not do that. All right. So lastly, I want to go over, well, it's not lastly. We've been talking a lot about samples and populations. And this is extremely important that we know the difference. Remember, you got an island. That's the population. If this is the only island that exists, that is the entire population. All of the little samples that you went around and you collected, sample 1, sample 2, sample 3, and so forth, are subsets of the population. So, in a sample, we know X bar is the mean, and in the population, we use the symbol mu. Mu. Okay? And this also means the mean. Now, once we get into inferential statistics, our goal is to take the data that we've collected, which are samples, and our goal is going to be to estimate what this population is. So if we have a sample mean, we will have a sample standard deviation. Okay. And we also have a population standard deviation. And it gets that symbol right there. So this is going to be the population. Some people just abbreviate population deviation. Other people call it the population standard deviation. So what I would like to do is give you the formula for all of these, okay? So real quick, we know X bar equals the summation of xi over lowercase n. The population mean, mu, is going to equal the summation of x all over capital N. This capital N is the population size. It's every single data value in that population. And if you cannot get every single one, then you're using a sample and you use lowercase n. If you look at these two formulas, they're kind of redundant. I get that. But watch how this standard deviation changes a little bit. So with a sample standard deviation, we have the square root of sigma times x minus x bar squared all over n minus 1. For the population standard deviation, everything looks similar, except our denominator is going to be capital N, which once again is our population size. Okay? So what I want to do now is just show you how to use SALT to do this. So let me go ahead and open up a homework problem real fast. All right, so let me open up this right here. So here I just have some measurements. They're just random numbers, that's all. Nothing too crazy. Okay? But to show you how to calculate the standard deviation using SALT, once again, we're going to go back to descriptive statistics. So we click on descriptive statistics. On the left-hand side, we have mean, standard deviation, the number of samples. And then if you scroll down just a little bit, you're going to see population standard deviation. So I'm going to click on that, and then I'm going to get rid of everything else. I don't need any of this stuff right here. And then off to the right, you can see here we have our mean, 4.75. The standard deviation. Now, this is the standard deviation of your sample. And you only have 12. So we're taking 12 minus 1, which is 11, to calculate this. So 2.7328 would be our sample standard deviation. And then off to the right here, you're going to see the population standard deviation. So I'm going to zoom in here a little bit. Let me scroll over. And that is 2.5207. So you can see how the sample standard deviation is different from the population standard deviation, okay? The larger your sample size gets, the closer in value those two numbers will become, all right? I think that's really important. So what I'm going to do is use my snipping tool. I'm going to copy and paste this into our notes. And I'm going to make that connection for us. So this is S. This is sigma. And as your sample size gets larger and larger and larger, those two numbers, 2.6 and 2.5, will actually start to get very, very close to each other. And if you had infinitely large numbers, those two numbers would be exactly the same. All right? So that's going to be it. Oh, no, that is not it. We need to go over range rule of thumb real quick. Oh, I almost forgot. All right, so we have this range rule of thumb. All right, so when we're collecting data, there is some data we would expect to find, and then there are other data values that we would consider outliers, okay? Now, the range rule of thumb that I'm going to give you, all right, has some advantages and then it has some disadvantages. One, an advantage. It's quick. It's awesome. It's just very fast. But because that it's quick, one of the disadvantages is you are sacrificing accuracy over simplicity. All right, this only gives us an idea. So this is based off the principle that 95% of our data would lie within 2 standard deviations away from the mean. What we're saying here is this. If we lived in a perfect world and we were to collect our data, you would have what we call a bell-shaped curve. Okay, so if we were to create a dot plot, you'd have all these dots, and they would just form this beautiful bell-shaped curve, okay? Now, let me do this real fast. There we go. And I need little dots down here and little dots over there. Okay, so right down the middle is our mean, okay? Now, what we would expect to find, and maybe some of you have heard this before, it's called the empirical rule. But what we would expect to find, let me use the letter S, that's fine, is that within 1 standard deviation away from the mean, so 1 above and 1 below, we would expect to find that of all the data we've collected, 68% falls within 1 deviation above or 1 deviation below. Okay? Now, if we extend this a little bit further, we would expect to find 95% of our collected data would be within 2 standard deviations away from the mean. So 2 above and 2 below. Okay? And then lastly, let me use a different color for this. We would expect to find 97.7% of our data would fall in between -3 standard deviations and +3 standard deviations from the mean. Now, in red, I'm going to highlight this. This is what we call usual, meaning these values that are in between 2 standard deviations away from the mean, are considered to be normal, not significant. So our range rule of thumb is defined as the range, So the range rule of thumb is defined as x bar plus or minus 2 standard deviations away from the mean. So if x bar equals, let's say, 10 and s equals 2, then we would expect that all our data falls within x bar minus 2s for my lower range of values, and x bar plus 2s for our upper values, or 10 minus 2 times 2, comma, 10 plus 2 times 2, which would be 6 and 14. So let's say we were talking about, I don't know. Really, off the top of my head, I don't know. Some stupid baseball. I don't like baseball at all. I think it's a boring sport. But that's beside the point. If you want to have an argument on why baseball is exciting, I would love to talk to you about it because I want to hear why. But let's say these are runs in a game. Okay, total runs in a game. For both teams. So what you're doing is you're just taking the final score and you're adding the two numbers. That's it. So if we found games that had 6 runs, I would say, okay, yeah, I would expect that. If we said we had games that had 13 runs, then I would say, yeah, I expect that. But if we had a game, if there was a baseball game where there were 21 runs, I would say that's suspicious. That's a little suspicious. Because 21 runs is outside of this range rule of thumb that we've just calculated. So I would say, that's an outlier. That's an outlier. That's not a normal thing. Okay? So, real quick, I just want to show you this because I know it's in our guided notes. So I'm just gonna scroll this over here for us real fast so you can see it. So right here where it says example stack crunch, this stack crunch thing, let me highlight it for us. That is the old statistical software package I used. You don't have to worry about that. Just cross that out in your notes. It's not a big deal. That was just how you did it using StatCrunch, which is, like I said, it's just a different statistical software package. We use Salt. Salt is a little bit different, but they all do the same thing, which is give you descriptive statistics. So I'm going to leave it off here at the end of this video here. I don't think there's any more we need to talk about. I will see you in the next one. Enjoy.